So this is our last normal lesson of the year, okay? Yeah! The 11th of May, True Protect Tuesday. You guys will be able to find and interpret measures of central tendency. We're finishing up section 12.3, okay? We're going to be finishing up this section. We're going to be doing a little bit of the homework of it. And then we're going to be doing the rest of the time reviewing today, okay? Does that make sense?
Yeah.
Okay.
Yeah!
Yeah. No. Yes, you can. I'll get it to you after in a bit, okay? All right. So last time, what we had done was we went through how to find the variance. We went through the long way of that. Do you guys remember that? Hey, you probably do, because that was the one where we said like we have to find the mean. And we said, hey, the mean was 92, and then we said, okay, well now we have to say the variance, which is that little like circle with a visor or like a sideways P or something like that, or sideways Q, excuse me, being squared. And we said, okay, well it's like 85 minus 92 being squared, plus 88 minus 92 being squared. And we had to keep doing that for everything, divided by 5, because there were 5 things. And we ended up getting the variance to be 29.2, and we ended up getting the standard deviation to be 5.4. And we said, hey, standard deviation is actually our most useful tool, most useful way to measure dispersion, to measure how spread out things are. Okay? And we said that can be important for different things. Did I talk about kind of like the sandwich thing in here? For restaurant, did I talk about that or no? Okay, sorry, I taught this a lot the last few days, so I'm just making sure I talk about different things in different classes. So, sometimes it's more useful to know stuff sometimes it's useful to know more than just the mean, more than just the average of something. Because let's say a restaurant hires me, they are making a new sandwich. They're trying out a new sandwich, they're seeing if people like it or not, seeing if they should stick it around or not, or just get rid of it. Okay, they're testing it out. And they say, hey, Mr. Kossel, can you see if this sandwich is a success or not? Can you see if it's worth it for us to keep it around? Okay. Well, for it to be worth it, they probably need to be able to sell a decent amount of them, right? Like people probably need to like it quite a bit, right? So let's say I send out a bunch of surveys, and I ask people to rate it, 1 to 10. What do you think of your sandwich? Would you buy it again? That kind of stuff, okay? And let's say the mean, the average, comes back at like a 7.5 out of 10. Okay, we'd say that's pretty good, right? And so just from that, you'd be like, oh yeah, people probably would get this again, kind of a thing. Because if a sandwich is at around a 5, are you probably going to order a sandwich again if it was like a 5 out of 10 for you? No, you're probably going to get something else you like more, wouldn't you? Like, you wouldn't be upset to eat it, but it's not what you would choose, is it? Okay, so it wouldn't make sense for them to have it if that's what the average is. Let's say the average is like 7.5. But it's also good to know, are these numbers all around the same thing? Did like just about everyone rate it at a 7.5? Or did like some of the people rate it at a 10 or a 9, but then also quite a few people rated it at like a 4 or a 5? That's a whole different thing. Because those that rated at 4 and 5, they're not getting it again. Those that rated it higher, they're probably going to order that thing quite often. So that's really good to know the information, because that can help you make a good decision on whether or not you should even keep the sandwich. Does that make sense? Okay, maybe a little bit. Okay, so that is one example of where this stuff could actually be really useful. Statistics is often said to be like, hey, you're taking math, but you're actually applying it to your real life. Okay, that's often what statistics ends up being, because how you interpret the number here, like how you interpret that, the standard deviation is 5.4. changes entirely upon what you're talking about. 5.4 can be considered to be a high standard deviation in some capacities, and a very low standard deviation in others. Now I want to remind you that a lower standard deviation indicates that the things are less spread out, they're closer together. Whereas a higher standard deviation means the opposite, they're more spread out, they're farther apart. And then at the end of class last time I said, hey, on the homework, we're just going to do the MAD, the mean absolute deviation. Not the variance or standard deviation, right? You guys remember that? Because I said, does anyone remember what I said about how we're going to do the variance and standard deviation moving forward? We're going to do it with a calculator to make it a lot easier than going through this long way with all of these numbers that we're going to type in, okay? We're still going to type in some numbers, but the calculator is actually going to do all the math for us, okay? How does that sound to you guys? Okay, yes. So, number 7. Here's what we do. Ignore these calculator steps. They're wrong. It's for this calculator, which we are not using. So for this calculator, which we are using, directly above the 8, if you go up like 3 numbers, you should see a button that says data. Don't push the button that says data. Don't push that yet.
I already did.
See it? Okay. Now above the button that pushes, if you push data, it just says stat error, right? Okay, if you get that, just hit clear. That's fine. Now above the data button, you should see in the second color, stat. You guys see stat there? Okay, that stands for statistics. So what I want you to do is hit second and go to stat. And you should see a couple options there. One is 1-var, the other is 2-var, and if you go even sideways more, you see one that's CLR data. You guys see those 2 different options? Okay, here's what they stand for. 1 variable, 2 variable, clear data. Do you want one of these calculators?
Yeah.
Okay. So that's what they stand for. 1 variable, meaning we're dealing with only 1 variable. Well, do you guys see do you guys see a scenario we're talking about? You're welcome. Both like time and money? No, we're just talking about 1 different variable here. So we're just going to go with the 1-var. 1 variable, hit enter. Then your screen goes blank, doesn't it? Now, do you notice at the very bottom of your screen, does it say stat now? That means we're in stat mode. We turned our calculator into a statistics calculator, okay? Does anyone not have stat at the bottom of their screen?
All I want for Christmas.
Yep.
There's a name.
Data.
Oh,
Yep. And you see now 1 bar. That's easier to see though. See how they got 1 bar? 1 variable. Enter. There's that. Does anyone else not have stat at the bottom of their calculator right now? Okay, what you do now, hit the data button. You no longer get an error. What do you see? X1 equals. Now, this is like an X sub 1. There's a little 1 underneath it, right? We've dealt with that before. It just means the first X. So here's what you're going to do. You're going to type in your first X value. 3. And you push, then you then you hit down, and it says FRQ equals 1. You guys see that?
Yeah.
That just says the frequency. How many 3s do you have? 1. Okay, go down again. What do you see now? X2. What do you think we're going to type into X2? 4. Go down. What do you think the frequency will be? 1. The next one, X3. What are you going to type in? 7. And what's your frequency? 1. X4. 8. Frequency of 1. X5. 11. Frequency of 1. X6. 12. Frequency? 2. Type in 2 and go down. On that one? On X12, on the 12th? Okay, so if you actually made a mistake, go back up. And then do you see it again? So if you go back up, you go to what you just saw previously. So, yep, so go down, and then change your frequency. So change 2. Yep, and then go down. Okay? X7, now it's 15. We can skip the second 12 because we put frequency of 2 on the last one. Does that make sense? Okay? Frequency of 1, and the last one, 19. All right, so now, all right, so now at this point, see, why did that not show up correctly? Okay, so now, once you have typed those in, go down again and it should be like an X9. You guys see like an X9? Okay, leave it blank. Hit data again. Hit data again. Did it just say calc and then go away?
Yeah.
Good. Did anyone not have that happen where it said calc and go away? Okay, Now hit stat var, the stat var button right next to data. Stat variable. Hit that button. Do you now see a bunch of options where it says n, an x with a bar over the top, a giant S with an X, and then what looks like standard deviation, right? With an X. Do you guys see that?
Yeah.
That's our standard deviation. The calculator just found it for us. The calculator just found our standard deviation for us. And what's it say it is to the nearest hundredth, aka 2 decimal places?
4.86.
4.86. That's your standard deviation. It found it for us. All that work we did last time, it did it for us. Mr. Kossel, how do I find the variance now? Well, how do you go from standard deviation to variance does it look like? You square it. So you take that number and you hit x squared. You hit the x squared button while you're highlighted that number, and it squares it for you.
23.6.
I would agree.
Oh, that's kind of cool, actually.
Isn't that cool? Okay, it does it for you. All you do is type in numbers. And it's like, oh yeah, let me do the work. Okay? Now, if you were to type in 4.86 and then square that, rather than squaring what was actually in the calculator, you'd get 23.62 rather than 23.65. Are those just barely different? I'll say that again. If you were to type in your calculator 4.86 and square it, rather than squaring the entire long number before we rounded it in the calculator, you'd get 23.62, which is just slightly different, and that's okay. Yeah, Brady. Okay. Now, fun fact, if you go back into to stat var, stat variable, you can highlight through n. How many things are we dealing with? We're dealing with 1, 2, 3, 4, 5, 6, 7, 8, 9 things. Does n say 9? Yeah. The x with a bar over it, that's the mean. The mean is 10.1. Repeating. You can see the sum, which is the, I think you guys have done that in like intro to business. Is that the class or no? What class are you guys using Excel in? What's the business class you're taking? Pure explorations. Are you guys doing like sum formula in Excel? Okay, so you guys know the sum symbol? Or no? It just says sum. Okay. The sum symbol looks like this. That's the sum symbol. Okay. So if you go over far enough to the next screen, you can see the sum of all the numbers. If you add up all these numbers, you get 91. Okay. So it just has all this different information in there. But really the only one we need right now is the standard deviation. Questions on that? All right. So now what we do, if we're done with that problem, we're moving on to the next one. We want to find the variance and standard deviation of the next one, number 7. You go into second, stat again. Second, stat. You see 1 var, 2 var, 1 variable, 2 variable. Go over 2 to the next screen. And you see CLR data. What do you think that's going to do? Clear the data. We're going on to the next problem. We don't need this data anymore. Hit enter. Now, that data is gone. Any questions on that? So what we do for the next problem is you hit data again because you're still in stat mode. And now we type in this data. And you don't have to put it in least to greatest. Your calculator will organize it just fine for you. Does that make sense? So then you type it in. You make sure if you have multiple of the same one, you put that in for your frequency. But do we have the multiple of the same one here at all? No. Don't have to worry about it. So type these in. Remember, when you're done typing, go down to the next X and hit data. If you need help on this at all, please let me know. All right, so what you should end up getting is your standard deviation to be 4.81. If you did not get that, we need to fix that issue right now, okay? And that's not a, like, oh, how dare you, okay? It's a, we're learning how to do this. This is your first time trying it on your own. It's fair to make a mistake, the kind of thing, okay? Did anyone not get that I already haven't helped? Okay? We're all good. So, now, you square it, and you end up getting 23.11 if you round to the nearest hundredth, 2 decimal places. Any questions on that? Alrighty. Okay, so, I want you to try number 8. Okay, I want you to try number 8. When you have it or have questions, raise your hand. Alright, attention back up here. Your standard deviation ends up being 32.22. Okay? If you take that and square it, Abby, what did you get?
1032.48.
Alrighty. Any questions on that?
1032.
Is that what you got?
No. I got
37?
I got 37. For what? Abby, what'd you do?
Oh, yeah, I got 37. I don't know why I said 36. Yeah, I got 37.
Liar.
Alright. Hey, happy we're paying attention, happy we're saying things, okay? Alright. Any question on that, guys?
Drugs.
Okay, how you guys feeling about that? Thumbs up, thumbs down. Okay, it looks like we're doing pretty well with it from what I saw, okay? And we're going to have more practice on that later today as well, okay? Let's go and move on to the next page. Into the next page.
Data distribution.
Okay, so data distribution. We're going to see the way data values are clustered. So, you can have 3 different types of distribution, okay? So you can have this first one on the far left where it's called positively skewed. Meaning the bulk of the data is to the left. You can have on the right where it's called negatively skewed, where the bulk of the data is to the right. And the last one, which we call a normal, I'll put it in apostrophes, distribution. We call it a normal distribution because this is saying, hey, most things are in the middle, and then kind of things go off of that. So this is kind of the average, and then about half the data is over here, half the data is on the left as well. Now, asymmetrical, and it's called asymmetrical bell-shaped curve, defined by the mean and the standard deviation of the data set. That's what we call the normal distribution. The area or space under the curve represents the probability with the total area being equal to 1. Because probability, we said that 1 is our same thing as 100% probability. And you'll see what I mean by a bell-shaped curve if you look right below, as we're about to be, with what's called the empirical rule. So this little curve here kind of looks like a bell, where it's high in the middle and it slopes down to the sides. So it's called a bell curve. So in a normal distribution, if things are distributed normally, with the mean and the standard deviation, the mean being kind of that weird U with the tail at the beginning, and the standard deviation being that O with the visor.
Mr. Schroeder walked by.
Okay. Approximately 68.2.
He's wearing pink and he's not Wednesday.
Approximately 68.2% of all the data will fall within 1 standard deviation of the mean. Saying, hey, here's the mean, here's the standard deviation, which we just found. 68% of the data, so over 2/3, will be within 1 standard deviation. 95.4% of the data is going to be within 2 standard deviations away. So if you go a little farther out, you're going to get about 95.4% of the data, almost all of it. And if you go within 3 standard deviations, you're going to get 99.8%. So almost all of it. That's like hand sanitizer killing 99.9% of germs. So if your mean is directly in the middle on this drawing here, the mean's directly in the middle here, to the right for 1 standard deviation of the mean, you'd have 34.1% falling within 1 standard deviation to the right of something. You'd have another 34.1% falling to the left. What happens if you take 34.1 and add it to 34.1? You get 68.2 that it's talking about there. Then, outside of that, you have another 13.6% falling between the first and second standard deviations. If you add up both 13.6s and both 34.1s, you get 95.4, falling within 2 standard deviations. So if this is the mean, 95.4% of the data is supposed to be inside of here. Then we have 2.2% in each of those. And so if we add up all 6 of these numbers so far, we end up getting 99.8%. And then we say there's an additional 0.1% on either side. So like barely anything. This is what is called the empirical rule. Most data distributions are going to follow this. Go right below this once you have this written down. Draw and label the normal the distribution curves, then answer the questions. So we have the weights of 50 football players normally distributed with a mean of 178 pounds and a standard deviation of 8 pounds. So in football, something that's pretty important to know is players' weights. It's often stressed in football that you want to get bigger, faster, stronger. Okay, so that way you can move people around, and then there's a lot of talk about what weight are you playing at. So the standard deviation is the mean is 178 pounds. So we put that number straight in the middle. Then the dashed line to the right of it is 1 standard deviation away. Well, what are we told the standard deviation is here? 8 pounds. So 8 pounds, or 1 standard deviation away from the mean, would be 186 pounds. Then you'd have 2 standard deviations away. So what's another 8 pounds away? 194. Keep going. And then what would be another, so 3 standard deviations away? 202. And we can go the reverse way as well to the left. Minus 1 standard deviation. If we subtract 8 pounds from our mean, we get 170. Do the same thing to the left. 2 standard deviations away to the left. 162. And 3 standard deviations to the left. 154. Now, according to our empirical rule, which we're going to utilize in this, what percent of the players weigh between 178 pounds and 194 pounds? How many players should fall in this category of these two according to our empirical rule right above? Right up above, how many would fall in this first little sliver between the mean and 1 standard deviation to the right? Isaac. Okay, the total would be for both of them 47.7%. Now, how we arrive at that is this is 34.1% and this is 13.6%. So because 178 to 194 covers that, you add them together, 47.7% are somewhere between 178 pounds and 194 pounds. That's about half of the team. A little under. Will fall somewhere between those two weights. So what's the probability that a player weighs at most 170? So does that mean they can weigh 178? No. It can mean they can weigh 170 all the way down to the left. So what's the probability that they weigh at most this? We have to add up all of these. So we add up the 0.1%, the 2.2%, and the 13.6%. And what do we end up getting? 15.9%. So what's the probability that a player weighs less than, at most 170? 15.9%. Pretty low. Most of the football players in this example are going to be heavier than that. Bless you, must rains on after us forget. What's the probability that a player weighs less than 162 or greater than 19.4? So it could be or greater than 194. So we have to do this and then also add this. And Eli is right. It is 4.6%. Because we have to also add in this 2.2% and this 0.1%. So you say, okay, less than 162, so these are the two categories less, and more than 194, these are the two categories more. Add up those four categories, and you get that. Raise your hand if you have any questions over the first three before we move on to letter D, or even how we label things. Okay, letter D. How many players weigh between 170 and 186 pounds? Well, in order to figure out how many players fall in this first standard deviation, 170 to 186, we first need to figure out the percent. So there's another 34.1% here according to the empirical rule. So how many percentage-wise weigh between that much? 68.2% of the players. How many players are there total? 50. So take 68.2% and multiply by 50. But how do you type percent into your calculator? Does anyone know? You have to move the decimal how many spots? 2 to the left. So we really type in 0.682. You really type in 0.682 because we move the decimal 2 to the left. And multiply that by 50. And can you have 0.1 of a player? No, so what would you call this then?
34.
You say 34 players of the 50 weigh between 170 and 186 pounds.
Can't you just use the percent button on the calculator? Above you push 2 and then you go above the parenthesis above the 8. And
Oh.
it does the same.
Oh, yeah, sure. All right, questions on that one before we move on to another example? Actually, see, that's the only example of that one we're doing right now.
Do we do this for
Yep. I'm kind of a stickler for labels. Yeah, I have labels. I'm a pretty big stickler for labels. I'm kind of known that way, especially in my geometry class. All right. Let's finish off these notes. Okay?
No.
Outliers. So let's talk about when in data sometimes we have what we call an outlier. It means it's a value that lies outside the other values. You kind of see how that's bolded, lie out, outlier. So let's say most of the values are right in here, but then we have a value way over here. Most people really like the sandwich, but there's one person who just had a crappy day and they really hated the sandwich. Most people really like this teacher, but there's one person that doesn't like that teacher. Most people really like whatever or hate whatever, but there's one person that really loves whatever. Okay? Does that happen? Okay? That's what we call an outlier.
Oh, like when a lot of people hated Miss Anderson, but there's like that one person that liked her.
Sure. Now, typically when something like that happens, okay, do you normally put much value to the one opinion that's different than all the others? Do you normally put much value to the one opinion that's different than all the others, or what do you normally kind of do?
Go to the majority.
You kind of ignore it, right? You kind of leave them out typically. That's often what happens.
Like Amazon
Okay.
reviews.
Like what?
Amazon reviews. Like
Okay? Yeah, like an Amazon review. When you see 5-star, 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 lots of good reviews, and you see like a 1-star and it's talking about like, this product was terrible for XYZ, whatever, but then all the other reviews are amazing. Do you put much weight in that one bad one? Not usually. You just assume the person had a bad day. Okay? Or that was one bad experience. Say, okay, well, that's not too bad. But if you see more and more of those, is that maybe something you give caution to? Okay? Same idea. So when we collect data, sometimes there's values that are far away from the main group of data. So we have to ask the question, well, what do we do with them? So we see here this number line. All these data values are here, and then we have one clear out between 9 and 10. That's our outlier. So let's say, for example, there's a long jump. Okay, and you guys see this on your paper here as well in front of you. New coach has been working with the long jump team this month. We have a track field going on right now. The athlete's performance has changed with the new coach. Augustus can now jump 0.15 meters further. June and Carol can jump 0.06 meters further. So a little bit of improvement. Here are all the results. Augustus improved by 0.15, Tom by 0.11, June and Carol improved, Bob improved. But what happened to Sam? He went down. Okay, so here are the results on the number line. We can see the mean of the data. And what happened to the mean of the data? Does the mean of the data show there's an improvement or getting worse? Getting worse. But is that fair to say that on average people got worse? No, but that's what the data shows. The data says right now, on average, people got worse. But that's just not true, is it? What's true is one person got worse, but most people got better. So the performance went down, so that tells us, well, the coach is bad. I mean, we need to get rid of this coach because they're making things worse. Well, so you need to think, why is that value over there? What happened to that value? What made it that way? Did they have a bad day? Did Sam maybe not feel well this day? Did he trip on the long jump? Or did he not quite have the right footing that he should have? Did he jump too early? Stuff like that. So that's all perfectly possible. Flip the page. So we saw what the outlier did to the mean, but let's see what it also can do to the median and the mode. So for this long jump, if we include Sam's value, the median, aka the middle left to right, is 0.085. Without Sam, it goes up a little bit. The mode, the most common value, it stays the same either way. So sometimes the mean and the median don't really change much, but the mean is what ends up changing. So sometimes you have to really look at why is that there? And maybe Sam's didn't have a bad day. Maybe Sam actually is worse with this new coach. Can that happen too? Sure, both could happen. But what needs to happen in a scenario where we do have an outlier, we need to take a hard look and say, well, why is it that way? Do these two people just not get along? Was it a bad day? Was it a good day? Was it the X, Y, Z? Go through all the factors and say, should we keep this outlier in here? Because sometimes, if you can say, oh, he's had a bad day, let's re-jump another day. Okay, you can kind of throw the outlier out and go with the rest of the information. But if you can't find a reason to actually throw it out and you say, no, he actually is worse now, then you can't throw out that piece of data. Does that make sense? Okay? And that's really a lot of what statistics is. There's no clear-cut answer of, oh, in this scenario, take it out. In this scenario, don't. It's very circumstantial, aka meaning it depends upon your circumstances. All right. That's actually all of our notes, believe it or not. Now, you guys do have that homework still. Okay, that orange worksheet. Go and take that out real quick. Go and take out that orange worksheet. Okay? You might have to do this, Jane. All right. Here's what I want you to do. I want you to spend the rest of class finishing this worksheet. So last time I assigned 1 and 2 to do the mean, median, modes, right? And I said on 3 through 6, just do the MAD, the mean absolute deviation. Now on 3 through 6, do we know a fast way to do variance and standard deviation? Yes. Oh my gosh, do we know a much faster way? Yes, okay? And so I want you to go ahead and do the variance and deviation for 3 through 6. And then go ahead on the back, do 7, 8, 9, and 10. Okay, go and do the back as well, okay? Now all of them. As I was reading, I'm like, why did I just read them out? This is all of them, okay? On the back there, on 7 and 8, It might be helpful to keep your notes out for this, guys. So that way, I put it away. So that way, you guys can write down the percentages there on that curve. Okay, does that make sense? All right. So go ahead and work on that there.